Let's Good morning everyone. Today we are going to learn about something called forced vibration. Has anyone ever played on the swing? Anna says that I love swinging. You push me and I swing back and forth. Perfect. When you push the swing again and again, you are applying a force repeatedly. This makes the swing move in a pattern we call vibration. Does that make sense? Yes. Swing keeps moving because you keep pushing. It keeps moving because you keep pushing. Exactly. Now imagine the swing likes to swing at certain speed all by itself. This speed is called natural frequency. It's your favorite rhythm to move. So if I push the swing at any speed, what happens? If you push slower or faster than the swing's natural speed, it moves, but not very high. So very high. But if you push exactly at its natural period, the swing goes higher and higher, and that is called resonance. Wow. So the swing listens best to pushes that matches its natural rhythm. Yes, the pushes add up perfectly. Now let's think about a spring with a ball on it. The ball can bounce up and down on the spring like a pogo stick. Exactly. If you let the ball bounce on its own, that's called free vibration. It bounces because you gave it a push, and then let go, right? So what if I keep tapping the ball gently and regularly? That's called force vibration. You are applying force again and again, making the ball bounce continually. So the ball bounces because of my taps, not just because I pushed it once. Yes, right. The total movement is a mix of two parts. One is the transient bounce from the first push, and then the steady bounce caused by your tapping. So which part lasts longer? Good point. The transient bounce fades away with time, especially if there's a friction or air resistance. The steady bounce keeps going as long as you keep tapping. So which part lasts longer? The transient bounce fades away with time, especially if there's a friction or air resistance. And the steady bounce keeps going as long as you keep tapping. What if I tap faster or slower than the ball's natural bounce speed? If your tapping is faster or slower, the ball bounces, but not very high. But if your tap matches with the ball's natural bounce speed, the ball bounce gets bigger and bigger. That's resonance again. Why does that happen? Imagine pushing a swing at the exact right time. Each push gives it more energy, making it go higher. If you push at the wrong time, your pushes don't help us much. So which part lasts longer? The transient bounce fades away with time. So initial push, whatever you are given, that fades away with time, especially if there is a friction or air resistance. If there is a damping, that's going to remove the energy from the system. That's why the vibration fades out over some time. It's dying down. If there is no damping, the vibration would never die down. It would keep on going. It would go forever. But it's in practical life, there is a damping or friction resistance everywhere. That's why the transient bounce fades away with time, especially if there's a friction or air resistance. The steady state bounce keeps going as long as you keep tapping. As long as the force acts on it, the vibration will continue in case of forced vibration. Technical report: forced vibration without damping. Forced vibration is a fundamental concept in engineering dynamics where the system is subjected to an external periodic force during its motion. Unlike free vibration, where the system vibrates due to its initial energy, forced vibration involves continuous excitation by the external force. There is a continuous excitation by the external force. that's involved in the forced vibration. This report analyzes the forced vibrations without damping, focusing on simple spring mass system subject to harmonic excitation. Problem definition, physical model. Consider spring mass system and subjected to a harmonic forcing function, that's P naught equal to P naught equal to P times T equal to P naught into sine omega T. P naught is the amplitude of the forcing function, that's going with the constant. Omega is the we can say W, forcing frequency, omega we can say, and T is the time. The system is modeled as shown below. The spring mass system subjected to harmonic force. The governing equation of motion using Newton's second law. The equation of motion for mass under harmonic forcing without damping is mx double dot kx and p naught sine omega t. Xt is the displacement of the mass, and x double dot is the acceleration of the acceleration, that's the second derivative of the displacement with respect to time. Mathematical solution. This equation is the non-homogeneous second order ordinary differential equation. Non-homogeneous second order ordinary differential equation, mx double dot kx equal to p naught sine omega t. The general solution xt consists of two parts, x of t equal to xct and xpt. xct is the complementary solution, homogeneous. xp of t is the forced or particular solution. The solution to the equation has two parts. One is x of t equal to x transient t and x steady t. X transient is the transient free vibration that starts with initial conditions and fades away because of damping. X steady of t is the steady state force vibration that happens due to the continuous external force. What does the transient part look like? It looks like this. Transient equal to e power minus gamma omega n t in bracket c1 sine omega dt plus c2 cos omega dt. The exponential e power minus gamma into omega n t. That means the amplitude shrinks over time because damping removes energy. What about the steady state part? The steady state vibration is x of t equal to x into sine omega t minus phi. X is the amplitude of vibration at the forcing frequency, phi is the phase angle, showing how much the vibration lags behind the force. Alright everyone, today I want to focus more on transient response. That's the part of the vibration that happens right after you just start pushing or disturb the system. Is that part that goes away after a while? Yes, exactly. When you first push a mass on a spring, it does not immediately settle into steady vibration. Instead, it wiggles in a special way, that is a transient response. Remember, the full displacement equation with the damping is x of t with equal to e power minus gamma into omega n t, c1 sine omega dt, that's omega dt is the damped frequency, and c2 cos omega dt plus x into sine omega t into minus phi. The first part, that's the transient response. Why does it have the exponential thing? E power minus gamma into omega n t. Why does it have the exponential thing? In this formula, there is something exponential is there, right? E power minus omega n d. Why does it have the exponential thing? Why does it have that exponential thing? That exponential thing shows that vibration dying out over time. What does it mean? Like it's dying out, vibration is dying out over time. The factor gamma into omega n controls how fast it fades. More damping means it disappears very faster. Why does it have the exponential thing? The exponential shows the vibration dying out over time. The factor gamma into omega n controls how fast it fades. More damping means it's disappear faster. Okay, what about sine and cosine terms? Why do we have those terms? Those describe the shape of the vibration. Because of the damping, the vibration does not stay at natural frequency, but the damped natural frequency, that is which is a bit slower. Why is it slower? Why is it slower? Damping pulls back the system, reducing the frequency of vibrations, free vibration slightly. So complementary solution, setting right hand side to 0 in m x double dot c x e plus k and x equals 0. That's a characteristic equation, we can get it, and from this we can find out the natural frequency omega n equals square root of k by m. These things are, it's okay, these are just formulas. It is the natural frequency of the system. C1, C2 we need are the constants determined by the initial conditions. This is a particular solution. This part comes just because of there is a forcing frequency. If there is no forcing frequency, you will not get this particular solution. It means like if there is no external force, you will not have this particular solution. Only the transient response it will come. That depends on only the natural characteristic of the structure, mass and stiffness. The transient response is due to the initial disturbance to the structure, but the particular solution is like it's like a force continuously acting on the structure. If you, for example, that ball problem, if you keep tapping the ball, it keeps moving. If you don't keep tapping it, the ball won't move it. There will not be any vibration. The initial displacement, whatever you give it, and then if you don't give the continuous force, like forcing periodic force, if you don't give it, the system is not going to vibrate anymore, because the transient response fades away after some time due to the damping. Okay, so the particular solution, if you see, this is like a forcing frequency, xp of t equal to a sine omega t. Now substitute into the differential equation, you can simply get it the amplitude becomes p naught divided by k into 1 minus beta squared. Beta is nothing but the omega into omega n. That's a frequency ratio. That's a very important thing. Frequency ratio, if you see like our forcing frequency w, if it close to wn, that becomes beta ratio becomes 1, so 1 minus 1 becomes 0, so the denominator becomes 0, so the amplitude goes to infinite value. But in reality there is always damping, so it would never go to the infinite value. Amplitude comes down. It's all depends on how much damping is present. If the damping is so high, the amplitude comes less and it becomes broader. It does not spike at the resonance value because of damping. If there is no damping, it goes to infinity. The amplitude goes to infinity. So static deflection and amplitude relation. If P naught were applied as a static force, the static deflection delta st would be like delta st equal to p naught divided by k. Hence the amplitude of force vibration becomes a equal to delta st 1 minus beta squared. The general solution and physical interpretation. The total solution is x of t is c1 sine omega in t plus c2 sine cos omega in t plus delta st into sine omega in t by 1 minus beta squared. The first two terms, c1 c2, those terms are the right. That's related to the free vibration. There is nothing but transient response. Depend on the initial conditions and the system parameters. In real systems, those decay due to damping. The third term is the steady state or forced vibration that persists as long as the external force is applied. So vibration is lasting as long as if the periodic external force is applied. If there is no periodic external force, vibration is not going to be there. So resonance phenomenon. At resonance, beta equal to omega by omega n equal to 1. That means denominator 1 minus beta squared becomes 0. So amplitude becomes infinity, implying theoretically infinite amplitude of vibration. Physically, this leads to a very large oscillations which can cause structural failure. The magnification factor quantifies the amplification of steady state amplitude related to static deflection. So magnification factor A by delta S equal to 1 minus 1 beta squared. Often this is plotted to show the effect of forcing frequency or amplitude. Summary and conclusion. If you see, the force vibration without damping is modeled by a linear second order ordinary differential equation with sinusoidal forcing. Solution combines transient free vibration and steady state force vibration. Forced response amplitude depends on the forcing frequency related to the natural frequency. At resonance beta equal to 1, amplitude theoretically becomes infinite, indicating a critical condition. Damping not considered here is essential in practice to limit amplitudes and avoid catastrophic failure. Good morning. Today we discuss forced vibration without damping. Anyone know what forced vibration means? Is it when the external force keeps pushing the system? Yeah, external force keeps pushing the system, exactly like harmonic force, P equal P naught into sine omega t. What do you think happens if the force frequency matches the system's natural frequency? Does it vibrate more? Yeah, like resonance. Yes, resonance makes the amplitude grow very large. What do you think that is? What do you think that is? Because the system keeps getting energy at just the right time. Because the system keeps getting energy at the just right time, right? The energy adds up mathematically. Amplitude A equal to delta STP1 minus beta squared, with beta equal to omega by omega n. What happens? Beta equal to 1 division by 0. That means like amplitude becomes infinite in theory, yes, but real systems have damping. Without it, damage can happen. Why might damping matter? Why might damping matter? Reduces vibration, stops amplitude from growing too much. Exactly, that's why engineers design damping systems. Any questions? How do you find constants in the solution from initial conditions? They affect the transient vibrations, which fade away over time. The steady state remains. Clear? Yes, Professor. To solve this equation, we split the motion into two parts. One is free vibration, how the ball moves if you push once and let go. How the ball moves if you push once and let go, that's a free vibration. Forced vibration is how it moves when you keep tapping. How it moves when you keep tapping it. The free vibration is xc c1 sin omega t into plus c2 cos omega t. Omega n is the natural frequency of the system. C1, C2 depends on initial conditions. What about the forced vibration? We guess it looks like the sine wave matching with the tapping force. Xp equal to A sin omega t. Substituting the equation, we find P naught equal to P naught divided by K into 1 minus beta squared, where beta is the frequency ratio. This means amplitude depends on how close the tapping frequency is to the natural frequency. Today we will study the full vibration motion of a damped mass system under periodic force. I remember there are two parts. One is transient, another is steady state. The total motion is x of t equal to xc t plus xpt. Xc is the transient response, xp is the steady state response. What's the difference? The transient is the initial vibration right after force starts. It fades away due to damping, and steady state is what stays after transient dies out, a steady vibration matching to the force frequency. Can we look at the math for each? Let's define the system. Mass equal to m equal to 1 kg, spring constant equal 16 Newton per meter, damping ratio 0.25, forcing frequency 3 radians per second, force amplitude 5 Newton. First, find the natural frequency omega n equals square root of k by m, that's 4 radians per second, and damped natural frequency omega d is equal to omega into 1 minus damping ratio square, that becomes 3.87 2 radians per second. What about the transient response? So the transient part is x of t equal to e power minus gamma into omega n t c1 cos omega dt plus c2 sin omega dt. This describes vibrations that decrease over time because of damping. This describes vibrations that decrease over time because of damping. How do we find C1 and C2? How do we find C1 C2? They come from the initial conditions. The initial position x of 0, initial velocity x naught of 0. What are those initial values? Let's say initial position x of 0 equal to 0.1 meter. The system is pulled 0.1 meter initially. Initial velocity is 0 meter per second released from rest. So at t equal 0, the transient displacement x naught of c equal to c1. So since e power 0 is 1, cos power 0 is 1, sin power 0 equals 0, sin 0 equals 0. So c1 equal to x of naught equal to 0.1. So what about c2? We differentiate x of t to find velocity. So this is the differentiation using the product rule. So at t equals 0, this simplifies to x naught of c equal to minus omega n c1 plus omega d c2. Since x naught 0 equal to x that c 0 equal to, we solve for c2. C2 becomes 0.0258. So the transient response is C of t e power minus 1t 0.1 cos 3.78872t plus 0.0258 sine 3.872t. What about the steady state part, xp of t? The steady state solution is xp of t equal to x sine omega t into minus phi. X is the steady state amplitude, phi is the phase lag angle. How do we find x? To find first find the static deflection. Static deflection equal to p naught by k, that's a 5 divided by 16, 0.3125 meter. Next, frequency ratio, beta equal to omega by omega n, that's 3 by 4, that's forcing frequency divided by natural frequency, 0.75. Now the amplitude we can find it out, x equal to delta st by square root of 1 minus beta square whole square plus 2 eta into beta whole square. So once you substitute everything, then we will get the x value that becomes 0.542. So here we can see amplitude x equal to 0.3125 divided by 0.576 is 0.542. So what about the phase angle phi? We can use the phi formula. We can find out the phi is 40.6. So the steady state part is xp of t 0.542 sine 3t minus 40.6 degree. How do we combine both parts? The total motion is x of t equal to xct plus xpt. So once we put this one, it becomes the complete solution. So at the start, the transient vibrations make the system wiggle a lot. Yes, the transient oscillations depend on the initial conditions and gradually disappear because of damping. So the transient response gradually disappears because of damping, and after a while only the steady state vibration stays. Exactly, that's the vibration at the forcing frequency with constant amplitude and phase lag. This helps me see the full picture of the system's motion over time. Great. This understanding is important in engineering to predict and control vibrations. Can we try plot this next time? We will visualize the transient decay and steady state vibration together. So what is transient decay? When a damped system is set into motion, the initial vibration is called the transient response. That don't last forever. Instead, they shrink or decay over time because the system loses energy, usually due to the friction or other resistance. That's a transient decay. Why does transient decay happen? The system has a damping force proportional to the velocity. This damping force removes the energy from the system as it vibrates. Because energy is lost, vibration amplitude gets smaller and smaller. Because energy is getting lost from the system, so amplitude also comes down and gets smaller and smaller. How do we describe the transient decay mathematically? The transient response looks like xc of t equal to e power minus eta omega n d plus into c1 cos omega dt c2 sin omega dt. E power minus omega n dt, that's the exponential decay term. Eta is the damping ratio, how strong the damping is. Omega n is the natural frequency, how fast the system wants to vibrate without damping. Omega n is the natural frequency, how fast the system wants to vibrate naturally without damping. Omega d is the damped natural frequency, the actual vibration frequency with damping. C1, C2 depend on how the system started moving. What does the exponential term do? The term e power minus eta into omega n d, that shrinks the amplitude over time. That's the decay. So at t equals 0, that means e power 0 equal to 1. That means no shrinking yet. As time t increases, the term gets smaller, making the vibration amplitude smaller. Eventually t becomes infinity, e power minus omega n t becomes 0. So the transient response disappears. At infinity time, the transient response disappears. How fast does it decay? The rate of decay depends on omega eta into omega n.
Larger values means faster decay. Example, eta is 0.25 and omega is 4 means eta omega is 1 per second, right? So this means after 1 second the transient amplitude is about e power minus 1, that is 0.37 times original. That means 37%. After 1 second it becomes almost 37% is lost. Energy is almost it's gone out. Only it being not 37% lost, it's almost 73%, 63% is lost. Only you are getting only 37% is available. After 1 second it's like you imagine like now we have the battery 100%. Okay, after 1 second the battery becomes 37%. After 2 seconds it becomes only 14%. After 3 seconds it becomes only 5%. Within 3 seconds your battery goes from 100 to 5%. How does it you feel? Like it's decaying rapidly like anything, right? But that's what it happens like. But just to becomes zero it becomes infinite time. So that's a different issue. So visualizing the transient decay, imagine a swinging pendulum slowing down. Each swing is smaller than the last one because the friction takes energy away. The vibrations height drops exponentially. Transient decay means the initial vibrations fade away over time. This happens because the damping removes energy from the system. The decay follows the exponential curve controlled by eta omega n. After enough time, only the steady state vibration remains.